Alright, in this video I'm going to help you to solve problems 767 and 768. Let's go first with problem 767. In this case, we are asked to design a hydraulic fracture completion job in the Barnett Shale, for which we have the depth and the pressure at the point in which the horizontal wellbores are going to land. The first question is the direction of those horizontal wellbores. Let me first do just a quick cross section. So this is going to be the wellbore, and the depth of the lateral is 8,200 feet of true vertical depth. So this is in the Barnett Shale, so remember this is onshore. All right, but now what is going to be the orientation of this wellbore in the geographical coordinate system? In which direction are you going to drill it? Well, for that you need to know what is the minimum principal stress direction in this location. And in order to do that, here I'm providing you with a link of the stress map of the US. If you click in this link, you're going to get into this picture that shows the state of stress in the US. The direction of the lines tells you what is the direction of SH max. So for example, here near the Barnett, SH max is going in direction more or less, let's say 30 degrees from the east towards the north. And also you could use alternatively this other map that I also like a lot. This is in chapter 2. Here also, for a region close to the Barnett Shale, you can observe what is the direction of SH max. If you know SH max, you know what the direction of SH min is, right? Because SH max is going to be perpendicular to SH min. Once you know the direction of SH min, you should be able to tell me in which direction you're going to drill your wellbore. In the direction of SH min, in the direction of SH max, or something in between. That's what is discussed in the notes before. But in order to maximize the drainage area, there's going to be just one solution. All right, so after you do that, I like that for number 2, you sketch, this would be just a side view where your fractures are going to be here and there. I'm just asking you to sketch these, assuming that these are all planar fractures and a single fracture out of each stage. In the next point, I'm asking you to sketch a horizontal well from a top view. So how would this look from a top view? Please, when you do that, consider that this is going to be the north, this is going to be the east, and I like to see in this top view the actual orientation of your horizontal wellbore, where those fractures are respecting the geometry that I'm telling you over here. With 10 fracture stages, just one perforation cluster for each stage, with the dimensions that are mentioned over here, including the fracture half length. And the last point is to calculate what is the minimum pressure needed in order to propagate this hydraulic fracture. Basically, this comes down to calculating the value for which P net is more or less equal to 0. So I don't know why I did that. Just give me one sec that I fix it. Okay. Okay, so in C, I'm asking for the minimum value of the pressure for this fracture to propagate or to open. And that means that a value for which the net pressure is going to be equal to more or less 0. And we know that net pressure is equal to the pressure in the fracture minus the minimum principal total stress. So if this value is equal to 0, what I'm really asking for here is for the value of the minimum principal stress S3. And for this particular case, I'm going to give you a hint. In the Barnett shale, the minimum principal stress is horizontal. Therefore, S3 is going to be equal to SH mean. And what I'm asking you is to find out what SH mean is, because that's going to be the minimum pressure required for do a hydraulic fracturing completion. And you do know how to compute SH mean. We have been doing this for the entire course. And here I offer two solutions possible. One will be that you estimate SH mean with equations of elasticity, and that would require using Poisson ratios, and here you don't have any tectonic strain, so you just need the Poisson ratio and the vertical effective stress and the pore pressure, and you should be able to do that. And also you could do this assuming equilibrium of faults or plasticity, and that would be the minimum possible value of SH mean for this condition, assuming an equilibrium of faults on a parameter Q which is equal to 3.5. Just to refresh your memory, this one, in this one, sigma in general is going to be proportional to a strain and a Young modulus and a Poisson ratio. In here, in plasticity, the maximum principal stress is going to be equal to Q times the minimum principal stress. So if you know what this is, you can calculate that one. So either method that you use is going to allow you to calculate what is the minimum pressure in order to do this hydraulic fracture completion. And this is very important because once we add the net pressure, that gives us the total downhole pressure in order to make this hydraulic fracture treatment. If we know what is the total downhole pressure and also we know the depth of this particular fracture treatment, also we can tell what is the surface that we need, what is the pressure that we need on surface to make such hydraulic fracturing job, which usually these pumps, I'm not asking for that calculation in here. I should add it. Next year probably you'll have it. But if you know all of these properties, that can help you design your pump on the surface to know what is the pressure that you need on surface in order to do the hydraulic fracture completion at a given location. Usually this surface pressure is in the order of a few thousand psi. That's the range of the pumps that it's required to perform a hydraulic fracturing job. All right, that's for problem number 767. There's one more thing before I forget. For number D, I would also like that you draw the path of the Wellbore orientation on a semi-sphere projection or a Stereonet projection. So that means that if you have a Wellbore, here I'm just drawing a side view that goes from the surface. I don't know why I drew that in that side. So if you have a Wellbore that goes from the surface as it's been drilled to a location you're going to go from vertical to horizontal. And you can map that in a Stereonet projection where this is the north, south, east, and west, right? And I encourage you, if you don't remember this, to check the notes about deviated wellbores, and you will see that you can map each section of the wellbore. Let's say if I grab this location from here to there, I can map that in the Stereonet. And as I go into deviations from verticality, that's going to show up somewhere else over here. And that's what I want you to do. This is going to depend where these points locate. They are going to depend in which direction the wellbore is drilled. So this comes back to part A and part B. So be mindful of that. I'm going to give you one more hint. Once it goes into the horizontal trend, it's going to be somewhere here in this outer sphere. All right, now let's go to problem 768. Problem 768 requires that you are able to interpret and understand a microseismicity plot or a microseismicity figure. And here I have one example that I took from this publication that I encourage you to read if you are interested into microseismicity, in which we have a path on surface, and on the surface we have the wellbores going from vertical to horizontal, and we have three wellbores. The green one, the red, and the yellow. Here in the caption you have more details about which is which, and also a little bit more of information about the fracturing. For example, this was done with zipper style. Here also we see superimposed with the orientation and the trajectories of the wellbores, we see also the clouds of microseismicity for different stages. You have here the labels on the right. So I'm asking you here to interpret a few things. First of all, information related to the wellbores, and then information related to the microseismic volume and to the resulting stimulated reservoir volume. For the first question, it's what is the length of the laterals? And that's more or less straightforward. So number A, I'm asking what is the length of the laterals. Here, this is a distance in feet. So more or less, this grid is, well, it's not more or less, but exactly 400 feet by 400 feet. So these squares are more or less the size of let's see, 4 or more. Actually, 4 by 4. No, more or less. Let's say a big field in a stadium, a football field with everything that it's that is around the football field. So the tribunes, everything. Okay, so if this is 400 feet from line to line, then you can tell me more or less, I'm not asking you for a precise number, but more or less what is the length of the laterals. So you compare that to the values that we mentioned before. That's the first question, length of the laterals. I'm also asking you what is the spacing between the laterals. It's not the same in the two cases, so just provide a range for that. And you should also keep in mind that for the spacing, that these wellbores are not at the same height. Wellbore 1H, which is, let's see, which is 1H? 1H is the red one, is higher in elevation than 2H and 3H. So if you want to compute the actual spacing, not horizontal spacing, but absolute spacing in diagonal between each wellbore, you're going to have to use the Pythagoras rule in order to do that. But it is just a geometry. Okay, so this is number A, and number B, I'm asking for more or less to tell me what is the strike of the hydraulic fractures at the toe of the laterals. So the laterals are these wellbores, right? The toe would be over here at the tip of the wellbore. Remember, these are called the heel and the toe with an analogy of a foot. So if we had a foot over here, let me draw it here on the right. This analogy is, if this is a foot, this is I always make this mistake. This is the heel, these are the toes. So this is the toe of the wellbore, this is the heel. So I'm referring to these sections, so these stages. And you can more or less see a trend in the microseismic cloud, right? It's not very definite because we were saying that these microseismic clouds, they do not map exactly where the fracture is, where the hydraulic fracture is or the main hydraulic fracture is, but it just gives you a trend. So I hope that you see that more or less there is a trend. If I look, for example, at the red cloud, that tells me what is the orientation or the strike of the hydraulic fracture. These are vertical fractures, so the strike is going to be along this line. And if you know that this is the north, you can tell me exactly what that strike is, or not exactly, but approximately what the strike of that hydraulic fracture is. And from here also you can compare also the strike, expected strike of that fracture or orientation of that fracture with the one that you get from problem number 7, because actually this image comes from the Barnett shale, and the Barnett shale is what you are also solving in problem number 7. So after you solve this problem and you find out what is the ideal orientation of a wellbore at that location and what will be the expected orientation of the hydraulic fractures at those locations, you can compare that. You could compare that with these results and the orientation of this microseismic cloud, where the trend is going to tell you more or less the direction in which the hydraulic fracture is growing horizontally, and it's going to tell you what the strike is. From here, also you could interpret what is the fracture half length. Notice that if I consider the case of this fracture, which is growing out, this is 3H, is growing out of a wellbore 3H, and 3H is the yellow, the red cloud. You could tell from here what is the fracture half length. And notice in this case that it doesn't have to be symmetric, right? Because it looks like it's growing more towards the southwest direction than towards the northeast. In reality, many of these fractions are not symmetric, and this is the case that you can see in here. So just give me an approximation of more or less what is the interpreted half length out of this microseismic volume. And assuming that this microseismic cloud reveals what the stimulated reservoir volume is, I'd like that you compute what is also the estimated ultimate recovery. You know what is the area. Just from looking at this plot, you can calculate the area more or less of this microseismic cloud. Here I'm just doing that more or less approximately as in a square following the mouse. If you multiply this area times the thickness of the formation, that's going to give you the total reservoir volume, right? If you multiply that total reservoir volume times porosity, that's going to give you the pore volume. If you multiply that pore volume times 1 minus water saturation, that's going to give you hydrocarbon volume. If you multiply that hydrocarbon volume times now the recovery factor, that's going to give you the estimated ultimate recovery. And you have that equation here in the notes, so I'm not going to write it again, but I'm just asking you to assume a porosity of 10%, recovery factor of 10%, and formation volume factor of 1.2. So with that, you can compute an estimated ultimate recovery. Let me add one more thing here that I'm not going to ask you in the homework, but just for fun. Multiply that estimated ultimate recovery, which is the answer should be in barrels of oil, times the price of oil. That's going to give you the revenue without adjusting for net present value of this hydraulic fracture treatment. And you could compare also that to typical cost of a horizontal wellbore and completion, which is in the order of a few $millions for each, and then you will realize if probably this is profitable or not. All right, this is it for the homework.